We have all learned that two static charged particles have a potential energy and that the associated force between the particles is obtained by it is repulsive between two particles of the same charge, like two electrons, while particles with opposite charges, like an electron and a positron, attract each other. As a side note, try to remember the first time you were introduced to the electrostatic interaction. I bet that at that time you wondered why same charges repel each other while masses attract each other in the gravitational case. Then, like everyone, including me, you took this as an empirical fact and forgot that you eventually asked yourself the question. In fact, the answer to this question can again be found in quantum field theory. It tells us that the interaction between two particles is mediated by the exchange of a third one. For instance, the mediator of the electromagnetic interaction is the photon, noted gamma. The Coulomb scattering of two charged particles involves at least one photon exchange. What determines if the interaction is attractive or repulsive is the spin of the exchanged particle. The spin is an angular momentum which is intrinsic to the particle. Although it does not have a classical equivalent, it is often introduced as some sort of rotation of the particle on itself. Spins are all over the place in quantum mechanics, as you might see in later years. We eventually have to calculate some numbers. For that, it is good to remember that the charge of an electron is E equal minus 1.602 times 10 minus 19 coulombs. It is usual to include 1 over 4 pi epsilon 0 into E squared in the notation. For instance, the potential between two electrons is E squared over R with E squared equal 1.44 MeV times femtometers. We often use the fine structure constant alpha equal E squared divided by h bar c and equal to 1 over 137, which has no unit. In our unit system, the reduced Planck constant is h bar approximately equal to 197.3 MeV times femtometer divided by c.